You are doing a particular together project together, so that I can schedule your evaluation today. Who will send me? And send me the list of groups with the name and number of both the students. Fine. So I can see only 3 students in Goa campus. Any reason for their absence?
They must be on their way, madam.
So may we begin?
Yes, ma'am.
Fine. So we are now looking at the designing of maybe a system that is composed of op-amp. And in this we have taken the smallest application, that is comparator. A comparator is nothing but an op-amp. It's actually not a circuitry which is defined across an op-amp. Or you can make something like that. But then as it is, it's also is a comparator. Standalone op-amp is also a comparator. I can use it as a comparator. But when you design it as a comparator for comparing function, the design becomes little bit different. It becomes little bit different because now it's no longer an amplifier. I have to take care of it as its comparing abilities. So very simple, ideal voltage comparator. We start with the concept of ideal voltage comparator. So if this is a symbol of an ideal voltage comparator operating with a certain VDD, a single-ended output we are taking and a differential input we are taking. One of them may be a reference voltage with which you are comparing, other will be your input. So input can be less than the reference or input can be more than the reference. Accordingly, my output will be produced. So one time it would be a high going transition, other time it would be a low going transitions. Very simple. If I show it on try to draw its characteristic. So if this is Vin is actually the difference between the two terminals. Okay. So this is actually Vref minus the input that you are applying. That is the Vin to the comparator. That is the input to the comparator. And if input is positive, I can say V input is more than the V reference, then I will get a transition high, or it will be going to 0 or a low value. So I am trying to get a digital output, a kind of a digital output. Okay. So it compares two instantaneous values of two analog voltages and produces a digital output or a digital kind of an output. This is the operation or the requirement from a comparator. So normally where we look at accuracy of comparison operation, speed with which it does a comparison operation, how much power it dissipates, and some of the input properties like noise rejection ability, common mode rejection ratio, input capacitance, linearity, all these things. They also play a role in the design. Example is where we use comparators like in flash ADC, where we keep on comparing we have a resistor ladder. So we generate, suppose it's an 8-bit comparator, we generate 2 to the power 8 voltage levels. Okay, and then we compare those voltage levels with the input, and accordingly we generate a digital output, a bit pattern. So we have all these things are the comparators. So these thermometer code which is generated, we all know how the operation of a flash ADC works. Okay, so as if this input is more than the reference, I will get a high here, and below that all will be low. So all upper voltages will be high. No. All lower voltages will be high and all upper voltages will be 0. A kind of a thermometer code is generated, and this thermometer code is fed to an encoding logic, maybe a digital one, to convert it into a digital output. Maybe a pattern of 1 and 0. So this is a flash ADC working, and here we use extensively n2 to the power large number of comparators, depending on number of levels you are making. Okay, depends on how much is your LSB, 1 LSB. So let us see how to understand the design of a comparator in this. If I represent it as a block with a certain gain AV and digital input, not digital input, the difference in the inputs as V in, output as V out. So all I can say that delta V in, if delta V in is your difference between the two signals, output suppose goes to full VDD. So output changes to logic 1 or highest voltage. Let me say highest voltage is VDD. Then I can say delta V in is simply VDD by ABC. Gain of the comparator. Gain of the comparator. So if you have a 12-bit ADC, I have shown an example where you are working with a VDD of 1.8 volts and your full scale range is 0.9. Okay, so this full scale range 0.9 is converted into how many levels? 2 to the power 12, because it is a 12-bit ADC. So we have to create 2 to the power 12 levels, which is to be distributed across the entire full scale range. That is 0.9. My full scale range that I am taking here is 0.9. So 2 to the power 12 levels I have to create in this 0.9 voltages. So each difference is known as 1 LSB. So 1 LSB is simply, how much 1 LSB is simply 0.9 by 2 to the power 12. So in this situation, if I apply this voltage, what should be the gain of my amplifier? Now I am deciding the gain of my comparator. Output requirement is VDD and delta V in is, now if I am going for a half LSB precision, that is as long as your difference is till half LSB or less, output will remain 0. Output of the comparator will remain 0. If it is more than half LSB till full LSB, the output will go high. I am going for a half LSB precision. Okay, so maximum difference in the input should be only half LSB. It should be till half LSB. Differentiating mark is half LSB. If as long as half LSB is less than half LSB, output will be 0. More than half LSB, output would be 1. So half LSB to full LSB, again a difference of half LSB. 0 to half LSB, again a difference of half LSB. So maximum difference that we can have, that it can tolerate between its two inputs without changing its output, is half LSB. That is half LSB. So I can say now, if my input, as long as my input is till half LSB, okay, so at half LSB my output should go to 1.8. Below that, I would say it would be 0. So at half LSB, when the difference is half LSB, my output goes to full 1, so gain comes out to be 84 dB. So from the specification of my comparators, I am getting the specification for my amplifier. How to design this amplifier which is acting like a comparator? And suppose I say that comparator should have a design time, a comparison time of say 1 nanosecond. That is, I want my comparison operation to be within 1 nanoseconds. So how much should be my 3 dB frequency? Can you compute? If I give a total response time as 5 tau, so this 5 tau must be 1 nanosecond. This 5 tau must be 1 nanosecond, means tau must be 0.2 nanoseconds. So tau is inverse of 3 dB. So how much should be your 3 dB frequency? How much hertz? Loudly. 5 gigahertz. So accordingly I can get the bandwidth also. So now two things are very clear to me, that how much gain I should have for this 12-bit ADC and how much it should be my 3 dB frequency. And if I go for a single pole response, how much should be my UGB? If I go for a op-amp architecture which has a single pole response, which is acting like a comparator, how much should be my UGB? I am assuming a single pole response, transfer function. What should be the UGB, unity gain bandwidth? It would be gain times 3 dB. For a single pole response, it is gain times 3 dB. So gain is 84 dB. 3 dB is known to me. I know my UGB. I know my unity gain bandwidth. This is when I am assuming that I am going for a single pole transfer function. So now slowly I am getting the derivation of the parameter requirements for the op-amp that I have to design. And this op-amp now going to work as a comparator. This is going to operate as a comparator. Okay, so now we move on to the next. Fine. So you can either go for a single stage comparator, multi-stage comparator, or comparator with regenerative latches. That is mixing digital with that. Analog circuits mixing with digital. That is the use of cross-coupling. Regenerative latches. So you can go for a digital comparator is also fully digital. Also implementation is also possible. In a comparator, you can have a fully digital implementation also possible. Don't assume that only analog is possible. So you can work with both. You can actually work with both analog implementation as well as digital, or you can work with a mix of the two, hybrid structure. So comparator is something that can be a hybrid structure, can be fully analog, can be fully digital. It can be single stage, it can be multi-stage also. So various implementations now, various topologies are possible, I would say. As I was looking at topologies of amplifier, now I can have various topologies of comparator. Don't assume that different topologies for op-amp will be the different topologies of comparator. No, comparator can be entirely different topology also, because I can go for a hybrid structure also. I can go for a hybrid structure also. Clear? And amplification need not be linear, because all I want is a digital output. At any point of time, I do not require the gain or output to be A times input. I don't require that, because all I want is that the moment input is more than V reference, I should get a high output. Or input is less than the V reference, input should be low. That's all my requirement. At no point of time I design or I desire that it should always be a perfectly linear equation defined by V out is equal to A times V in. Not a very strict requirement here. It's not a very critical requirement. So I can design a comparator which may be operating in a non-linear way. May be operating into maybe going out of saturation. I don't care. Because I do not want my output to be a perfect replica of input. I don't desire. All I want is a logic high or a logic low. That is sufficient for me. So it may not be operating in a linear region. That's not a criteria now here, very strict criteria. That all transistors, they should operate only in the linear region. That's not a very strict criteria over here. Okay? So amplification need not be linear. Okay, and it need not be continuous in time also. Because my output is simply a digital output. I can even go for a sample system. I can even go for a sample system where I make use of switches. Where in one phase, one operation happens, then the switch opens up, another switch turns on, and something else happens. So I can work in stages. I can work in stages. It's not that continuous operation is required. All I want is that given the difference at the input, I should get a digital output. That's all. A continuous operation may not be required. So here, a very good use of analog sampled systems can be made, where you are using switches to perform 3 different operations, and output will come after 3 different operations. And 3 different operations are coming because of turning on and turning off of different switches. So you can have different phases of clock which are controlling these switches. You control the phases of the clock. Accordingly, some switches turn on, some switches turn off, and then slowly the circuitry moves from one phase to the next phase. And ultimately, after say n number of phases, which may be 2 or 3, you get your output. So comparators can be made clocked. Comparators can be made non-clocked. In a sample data system, it is going to be a clocked implementation, because switches will be controlled by a clock signal. So let us start understanding. So again, for any comparator design, what parameters we have to be critical, or what parameters will be critical to me in static. Under static conditions, gain, output high and output low states. How much should it be output high? How much should be, what is my VOL, what is my VOH? Input resolution, what's the minimum difference between the two input terminals which can be resolved? So input resolution, offset, because minimum difference is coming, so offset may change this minimum difference. Offset may change this minimum difference which can be amplified. And then the noise, because noise can also cause comparison to be faulty. Because you have an input referred noise voltage coming as an offset at the input. So difference between the two terminals you may not be able to resolve because it may be a noise signal. So all these things are becoming very, very critical from static point of view. From dynamic point of view, we are interested in the propagation, operation time. How much time a comparison operation takes? I want it a very speedy one. Clear? So naturally all the frequency response, slew rate, etc. will come into play. So going by the static characteristics first, draw the characteristics of a comparator. So difference in the input, V positive minus V negative. Two terminals are there. One of it will be your input, other will be your reference, with which you are comparing. So difference of the two inputs, accordingly your output will either go high or go low. If it is a dual rail, I will show it below 0. If it is not a dual rail, the entire circuitry will move towards in the first domain, in the first quadrant. In the first two quadrants, not third and fourth. Okay? So you may have a other way around. Suppose when difference is positive, your output is going low. When difference is negative, your output may go high. So you may have an inverting comparator, may have non-inverting comparator. Both ways you can design. Okay? So I define the gain of a comparator to be as given as the difference in the two output levels, VOH minus VOL, divided by the difference in the input signal. Now this is ideal characteristic. You never get this as an ideal characteristic, because this always have a slope. So the kind of practical characteristic that we obtain is this. So actually you get a kind of a slopy middle region. So change is slopy from VOL to VOH. It's not instantaneous, it takes some time. Okay? So it is similarly the change, the VIH. So it is taking some time, so it is only at this point it is attaining its full value. The logic one. So this I will say, this is the difference I will call as my V input high. That is at an input for which output will go high. An input for which output will go high. And I will call this as my VIL for which the output will go low. So in this situation, delta V in, this delta V will become VIH minus VIL. This much difference you require between your input terminals to change its state from low to high. To change the state of a comparator from low to high. Clear? So we are slowly moving towards practical transfer characteristic. And I would like this delta V, that is VIH minus VIL, to be as low as possible. Because even the minutest difference between the two terminals, comparator should be able to detect and then give you an output. I would like this delta V to be 0. Accordingly, my gain should tend to infinity. So it is desirable for my output to have, or my op-amp or comparator to have a very high gain. It is desirable. Not that I am amplifying. Not because I want a good amplification, but because I want a minutest difference between the two terminals to be detected. To be detected. Now this minutest possible difference that can be detected by the comparator is known as the input resolution. That's the minimum difference in the two input terminals that can be resolved by the comparator. This is called as input resolution. So input resolution is a very important parameter, very important parameter in the design of comparator. And that sets the gain of the comparator. Remember in 12-bit ADC we took this difference as half LSB. We took this difference as half LSB. But if you want to design a very accurate comparator, which is even able to create, remember the ADC accuracy increases the moment you increase the number of levels in the full scale range. I may move from 12-bit ADC to 20-bit ADC. If it is a 20-bit ADC, the number of levels you will have is 2 to the power 20. That means 1 LSB will be very small. That means 1 LSB will be your delta V. And to resolve that delta V, I should have a very high gain. That comparator should have a very high gain. So resolution decides the gain of the comparator. Resolution decides the gain of the comparator. So resolution is important. As a result, gain designing comes into picture. Resolution is important. So we define the minimum input voltage that is necessary to make V output as, now look here, this is my resolution of the comparator. So remember, minimum V in, currently do not look at V offset. Minimum V in, which is taken as a resolution, is simply the difference in the output divided by the gain. Simple. This is the mathematical definition of the input resolution. So minimum difference that can be resolved by the comparator. And now we include the effect of offset in our characteristics. Remember, the practical characteristic is this, where we are saying that this steep transition is not there. You always have a slopy transition coming to picture. As a result, we have a certain difference between VIL to VIH, which can cause the output to transit from VOL to VOH. We need a certain input value, that is not zero. This is what I mean by saying that there is certain VIL and VIH, that delta V is not close to zero. Okay, now if there is an offset, that's a kind of a zero error in your scale. What does this offset does? If already even under zero condition, zero input condition, you are getting a certain output, then what we do, we reflect it back at the input by dividing it by gain. Suppose I am getting a gain of output of 1 volt for a gain of 1000. So the minimum offset I am getting is 1 millivolt. That is as if I am applying a difference signal of 1 millivolt. As if I am applying a difference signal of 1 millivolt, plus minus. In that situation, for plus minus signal, plus minus 1 millivolt, I should discard the output, because it is not due to a valid signal applied. It is not due to a valid signal applied to my differential input. So I should discard the output. I must discard the output. As a result, if I have to give my input, it should be more than offset. As a result, my static characteristic, this static characteristic, it moves to either towards right or towards left. Depends on the offset, positive or negative. Depends on the offset, positive or negative. It shifts. What has happened? Goa campus, can you view the slides?
No, ma'am.
Just call the operator. Just wait, we are trying to call the operator. So you can draw the characteristics yourself, how to show the offset in your characteristics. Try to draw it on your own in your notebooks. You have to add the offset. That means your characteristic will shift towards right or left. Nature remains the same. Clear? So if I show you the offset, now look at the slides. This is how it has shifted towards the right. It can also shift towards the left. Okay? So now I have to give more difference. So your differential signal should be more than the normal value plus V offset. Plus V offset. So that means V offset decreases your resolution. Always remember. That is why we do not want any systematic offset. Remember, we tried to remove systematic offset from my design, op-amp design. Did we not? Then we said that random offset, which is because of mismatches, cannot be removed. So now we will look at how to negate the impact or effect of random offset. How to negate the effect of random offsets. So I will go for certain design technique, auto zeroing, in my comparator. Because you cannot remove offset, you have to only use a method of making it negligible. Some design technique you have to apply. So offset is going to play a very, very important role here. Because it affects your resolution. Now we come to the dynamic characteristics. As we said, dynamic means mostly the settling time. Mostly the settling time. Now comparator, if it is an op-amp, it can either operate in a linear mode or a slew mode. In linear mode, settling time is totally decided by the 3 dB frequency. Whereas in the slew mode, it is decided by the slew rate. In the slew mode, it is decided by the slew rate. Clear? So if your differential input is more, so that one arm is going to cut off, my comparator, which is an op-amp, would be operating in a slew mode. Clear? Now, so with respect to input, 50% value to 50% value of the output, this difference I am calling as my propagation time. TP, that is the time taken by a comparator to finish its operation. V 50% to 50%. The same definition that we are using in the digital. Clear? So now, if it is a dynamic characteristic, so we have to look at the response time, single pole transfer function. Okay, omega C will be your first pole. Single pole transfer function means only one pole. That means your time constant is tau C. That is 1 by tau C will be your 3 dB frequency. Clear? So now if I represent this in a time domain, I can say VOT, output voltage as a time. Simply it is going to be a charging operation, which is given by the gain times V in. Gain times, look here, V in. Okay, multiplied by 1 minus e to the power minus t by tau c. Charging equation. This charging equation, when you take it into Laplace domain, gives you a transfer function. Remember? It gives you a transfer function. Okay? So this is what we have got. Now VOT we are taking as the middle value of VOH minus VOL by 2. VOH minus, that's what we have just defined. Middle value of the two levels. So VOH minus VOL by 2, AV0 comes as it is. And what is V in? Simply VOH minus VOL by AV0. Resolution. Okay? I can get this from the resolution expression. V in. So I am taking V in as V in minimum. Minimum V in will be this value difference in the output divided by the gain. So simply substitute it in here. That is this value. Clear? Substitute this over here. And this is written as VOH minus VOL by 2. Simple substitution. And then you simplify. And then you simplify, you get your expression for TP. Because when this reaches its half value corresponding to this value of V in, the T will become TP. This T will become T. T propagation. So I get an expression for T propagation. When your comparator is operating in a linear mode, such that your dynamic characteristics are governed by 3 dB frequency. Your dynamic characteristics are governed by the frequency response or the 3 dB frequency, where I am assuming my comparator has a single pole transfer function. The expression for TP for V 50% value at the output is given by this expression. I have got an expression for propagation delay. This is for linear mode of operation. When both the arms of comparator is working. One arm is not going to cut off. Under that situation, I have got an expression for propagation delay. So propagation delay is given by this. So when will you get TP as TP max? So suppose your input is a step input. Suppose your input is a step input of V in minimum. So V input is a step input. Step input suddenly from 0 to V in min. So V in min and V in min cancels out. And then you simplify, it comes out to be tau C ln of 2, that is 0.69 tau C. Looks what? That this relation is familiar to me. 0.69 RC, remember? What is this relation? The relation we have been using in digital VLSI for computing the delays. When input is a step input. When our inputs are a step input. Suddenly the difference between the two terminals changed from 0 to a V in minimum. That is a minimum input, that is a resolution. Clear? So maximum TP you will get, so this expression will give you maximum propagation delay, that is this will be the smallest value. This will be the smallest value. But for V in more than V in minimum, your value will be more than this. Sorry, less than this. No. More than this, because it is maximum in the sense. No, I think I am doing the other way around. TP max, maximum TP you will obtain. So that means for any other value, you will get less than that. So this is worst case, maybe propagation delay time. Just go and check it out once again on your own. So in that case, as I said, if your V in is more than V in minimum, say K times. K can be any number, maybe twice, thrice, 4 times. Suppose your V in minimum is 0.1 volt, you are applying 0.2, 0.3, you are applying multiplying 0.4. So K becomes that multiple factor. K becomes that multiple factor. So you can define your propagation delay in this form. You can define your propagation delay in this form. So this is how you change, the value of TP will change. Look here. So this is in output changing from VOL to VOH. Output changing from VOL to VOH. And this is on the time axis. This is on the time axis. You will get a high output when Vin is more than Vin min. So slowly your output will charge. Can you see? So depending on the K factor, output either charges this way or it charges this way or it charges this. The slope, the speed with which it would be charging would be becoming less and less. So more the input, faster will be the decision. More the input with respect to reference, faster will be the decision. Closer the input with respect to reference, slower will be the decision. Slower will be the decision. Because when the things are very close, human mind also takes time to understand which one is larger. If one input is 1, other is 10, we do not have to think. Immediately we know output will be high or low. But if one is 0.32, other is 0.33, I take little bit longer to come to a final conclusion. Something like that. Something like that. So more closer the input to your Vin min, longer time it will take to decide. Longer time it will take to decide. That is what is shown here with this diagram. That is when Vin is closer to Vin min, the time taken by circuitry to come to a decision, that is charging towards high, is taking long time. This is taking long time. Clear? A very simple example, if your op-amp has this kind of a frequency response where your 3 dB is given as say 10 megahertz and FU is 1 gigahertz. Unity gain frequency or UGB is 1 gigahertz. We know F0 is simply, FU is simply gain times F0. So for 1 gigahertz or FU, F0 comes out to be 62 kHz. That is tau is coming out to be 1.5 microsecond. I will assume it to be very slow comparator, microseconds. The tau is coming in microseconds. Even though your UGB is FU is 1 giga, but no, that is not sufficient because 3 dB is very small. 3 dB is very small. So here 3 dB is more important than a UGB because this decides your speed in a linear mode. This decides your speed in a linear mode. Now we come to another operation of our op-amp. That is, what if op-amp goes to slew mode? Even then you will get your output. Even then you will get your output. Only thing is that your output will not be a linear operation. One of the arm is going to cut off in the differential pair. Okay? So we have now another expression for propagation delay. We have another expression for propagation time which depends on slew rate. So now slew rate is simply nothing but, remember, we define slew rate as dV by dV output by dt. So dt is the time taken for output to change by a delta V amount. Time taken for output to change by a delta V amount. Now if my output is changing from VOL to VOH, I know the delta V out. How much time is taken by delta V out to change its output from low to high or high to low? That is going to be my propagation time. That is going to be my propagation time. So we have got Tp as simply VOH minus VOL divided by 2. That is, we are taking V 50%. Our definition is for V 50%, changing from VOL to half of the middle or the middle point. Changing from minimum to middle point or maximum to the middle point. So half of VOH minus VOL. That is how we are defining our output. So that output swing divided by the slew rate. Divided by the slew rate, which comes out to be VOH minus VOL by 2 into slew rate. And we know how to compute the slew rate of the comparator. That we have already done. This we have already done. Computing the slew rate of a comparator. So this is one of the examples that I have taken on the book that I am referring to for this section is Allen and Holberg. CMOS analog circuit design by authors Allen and Holberg. Razavi does not discuss comparators. Razavi is not discussing comparator at all. So this entire chapter is from Allen and Holberg. Kindly note it down. So here is one example which shows how to compute the propagation delay for two different conditions, that is when op-amp is not slewing and another when op-amp is slewing. Kindly go through and you will understand. And remember, till now, my op-amp is never configured in a feedback mode. It is just an open loop comparator. At no point of time I am configuring it in a feedback mode. Remember? So I do not need any compensation. There is no CC requirement. I do not need to compensate my comparator, because it is an open loop comparator. Remember that. Now we come to, now till date it is only single stage comparator. Now we come to two stage. Slowly we are moving stage by stage. So whatever we have discussed, we are assuming there is only one stage comparator. Only one stage. Now you come to two stage. A two-stage comparator may have two dominant poles. It may have two dominant poles. Since it is open loop configuration, you do not need compensation. We do not need compensation. Simply a two-stage, as it is shown over here. A two-stage op-amp can act like a comparator. So first stage gain, the total gain will be gain of first stage, which is this, multiplied by the gain of second stage. So RO2 parallel RO4 is nothing but 1 upon GD2 plus GD4 in terms of conductances. I hope you understand this. Okay, now it will have two poles. It will have two poles. So P1, two poles will be there. So 1 upon RO2 parallel RO4 multiplied by CL. Or you will get GD2 plus GD4 in the numerator, divide by the C1, that means C capacitive loading present at the, over here. So this should not be in the denominator, this should be in the numerator. Conductance, it is a conductance, should come in the numerator. Similarly, the second pole will come at the output, or first pole may be at the output, second pole may be here. Depends. So pole at this node will be GD2 plus GD4. Pole at this node will be GD6 plus GD7. I'm not saying which one is coming first, because it depends on their RC combinations. Any one of them can come first. Any one of them can come first, then other will become second. But then look at the expressions. The pole seems expressions are nearly the same, R values will also be nearly the same. I assume that the poles will be close together. Both the poles will be dominant. The poles will be close together, so I will get this kind of a transfer function. I will get this kind, I am not getting a 0 here. The reason is, this transfer function does not contain a transmission 0. The reason is, I am not showing a 0 here. 0 exists or does not exist? 0 exists. Why? Because you have a CGD here. But CGD is so small that 0 moves towards infinity. Because we don't have a CC here. We do not have a compensation capacitor. It is only CGD. CGD is a parasitic capacitance, which is of very small value in femtofarads. So 0 exists, but it exists at very high frequency. It doesn't affect my UGB, gain bandwidth product. Okay? So now we have, again the minimum output may be 0, VSS may be 0. If you are working the dual rail, it may be minus a 2.5 volts. Or VSS may be minus 2.5, VDD can be 2.5. Or for a single rail, VDD can be 5 volts. And 0 can be, VOL can be 0. Accordingly, you have to make changes. Okay? So now you have to do a little bit of analysis. Step response. This I'll do little later. This I'll do little later. First of all, come here. So it has a two-pole response. For a single pole response, getting an expression for TP was very easy. It was simply tau. Mostly it was tau only. Okay? But for a two-pole system, the analysis becomes a little bit more involved. Because it has two poles. It has two poles. I have simply borrowed this expression. I have not solved it. That is time domain response of V out of t. It depends on the poles P1 and P2. Depends on two poles P1 and P2. These are P1 and P2 pole values. P1 and P2 pole values. There are two poles coming up. So I will get a transfer function in terms of omega P1, omega P2. Convert it back to, I can change from frequency domain to time domain very easily. And then I can get the function called VO of t. So remember, the transfer function gives you VOS upon V in S. You have to convert S to t. Move again from frequency domain to the time domain. We know the technique. Remember, Laplace transformations are known to you. Laplace transformations are known to you. You take inverse Laplace transformations. Remember? So you have to take the inverse Laplace transformation of this. And then this VOS upon V in S will get converted to VOT upon V input of t. Okay? So this is what you will obtain. You may check it out on your own by taking inverse Laplace transform of that function. So time domain representation of output voltage as a function of time depends on the two poles P1 and P2. Now you may have very rosy situation P1 equal to P2. We try to find out different ways of looking at the solution. What if the two poles are same? They come to the same location. So if P1 is equal to P2, this equation simplifies to this. This equation simplifies to this. And then we keep on simplifying, go on simplifying, and you will get your TP as this one. You have to keep on simplifying using binomial series, exponential series. This whole expression you have to go on simplifying. And ultimately you come to this expression. This is when you have a two-pole system. Expression of propagation delay when we have a two-pole system, which depends on the two poles. Here we have solved the equation when the two poles are same. Now the analysis will change when the two poles are different. That is, M1 is not, or P1 is not same as. Okay, so bell has gone. Before starting the new thing, that is slewing response for two-pole system, we'll start it next time. Okay.